Hello, welcome to another problem session. Today I have a relatively hard problem for you. See if you can do it. There are some simple ways to do it, so you may be able to find it. Okay, so let me present the solution now. So I'll draw a few pictures here just to understand what's going on. So let's draw a situation like that when a spring is fully extended. So, I mean, it's at this point there is no spring force. So this is a spring is in a relaxed state. So there is no spring force this side, there's no spring force this side, there is no normal force this side. Okay, now let's draw that picture, or this one, and this is t like 0 minus, just before, okay, release, just before release. So spring has been compressed and now there is this is your force, and the acceleration here is 0, which means there's a spring force. These are balancing. There is a spring force this way, and there's a normal force that way. So this is spring force, F, and all of them non-zero. Just aside, when a spring is attached to an object, it applies force on the two objects in this way. All right, and they're equal force, right? So so what's the force? The formula for the spring force is Fs, say is Fs equals to some spring constant, and if this is a length L and the net length is L0 when relaxed length is this will be K times L0 minus L. So spring force will have this absolute value, and then the direction depends on, if this was a x-axis, then this will be positive component x and this will be negative component x. So that's the spring force. So you will need that to do this problem. It's coming back to it now. So this is after you let go. Let's look at some this will be not there anymore. So this mass this is the only force, so this will accelerate. But on this mass you have both these forces and they will be still balanced. Okay, so initially there will be no acceleration, will be this. So let's look at another figure. So this is when the left edge comes up, then this acceleration is 0, but this acceleration is going that way, and there is only spring force here, and this acceleration 0 and the velocity was 0, so this is not going anywhere. So at some point it is going to come out here and it will be relaxed again, and the normal force, you can look at this, the spring force. Suppose this arrow says how big the spring force is, the normal force of balance. Over here the arrow will become smaller, and this normal force will be smaller. So at this point, the normal force will be 0, and spring force will also be 0 because acceleration is 0. But next instant, very next instant, you will see that this, as this thing is going, it still has a speed that way. Acceleration is 0, and it's going to go out there and then get pulled back. Over here now, at this instant, just an instant later, so acceleration is this way, which means spring force is this way. So a spring force on this is this way, so a spring force on this will be this way. And now there is no reason to have a normal force. It will start to pick up a speed now, and it starts to go to V. So what we want the time when this reaches this situation, right? So that's a setup, and let me now present you the solution as a setup. So I will write out. So this is arbitrary time t. You can we will set up equation of motion for this situation, and let's see, we're gonna just say from here to here, let's call this xb coordinate at time t, and let's write down the for xb coordinate, mass of b, xb coordinate, acceleration should be equal to the spring force on it, a spring force on b x component. So it's going to be on the right, so it's going to be positive k. And let's see, the original length is L0. So L0 minus x of b. So this is at time t. So this should be, so if we can solve this, so our strategy is solve this for xb of t, and then find t when xb of t equals to L0, right? So that's that's the strategy now. So how do we solve this? Well, let's call this x equal to this thing. We can say L0 minus xb. Okay, let, and then x double dot equals to minus xb double dot. And so put in there, I have a mb. We're going to call them equal masses, so let's call this just m. So let's call this mb is just m x double dot equal minus x double dot equals to k x. So this this will be x double dot equals to minus k over m x, and this is a simple harmonic oscillator equation. So the solution is simply x equal to a cosine omega t plus b sine omega t, and omega is the square root of k over m. Velocity is omega minus omega a sine omega t plus omega b cosine omega t. And now when we set x dot equal at time 0 is 0, that just makes it b equal to 0. So the solution is just this part. Solution is just that's the only part. So x equal to a cosine omega t. We need to find a. X at 0, x is L0 minus xb at 0 is equal to L0 minus wherever xb at 0 was L0 minus b. L0 minus L0 minus b. So L0 cancel out. So x0 is just at b. I could have just read that over there. So if I put this over there, that means a is just a b. Okay. So I have a solution. So there was a strategy. We found x of b. So x of b, using this, I get x of b at t equals to x of t L0 minus x of t, and L0 minus x of t is b, b cosine omega t, and omega is this thing, right? All right. And so we want to know when this is equal to L0. So we said this is L0. So L0 minus b cosine omega t. Say time is some big T at t equals to that t we want. This will be the case. That will means L0 got cancelled out, so b is not 0, so cosine omega t equals to 0. And the first time it will be when this is equal to pi over 2. Omega t equals to pi over 2. And so t is equal to pi over 2 omega, which is pi over 2 square root of k over m. Okay, so that's the complicated steps, but this is really a good problem because it illustrates a whole bunch of concepts here. So let's just go over one more time just to recap, because when I'm doing it, there's a lot of things that I did here. So first thing I did was to understand the problem vis-a-vis this equilibrium situation. And then I noticed that the problem of leaving the wall is actually a problem of finding this situation for this other block, finding the situation for the other block. You can do this problem when you just focus on center of mass motion also. There's another way to do this problem, and I wish I had time to illustrate that also, but right now it's already a lot of time for this video, so let me go over this approach. So let me just say do this using motion of center of mass. This you can do it by yourself, and you should, since you have the answer, you should be able to get that. Okay. So you have so problem was about this block, but I transferred that by looking at these pictures to the information about this block. And now that I isolated the problem, I was able to set up the equation of motion, and it was important to know the change in length is where this is another thing that people get confused about is spring force is not length but change in length, and then it becomes just a math problem. After that, it's just a straight math problem, and once you solve the math problem, it's not that difficult to solve the math problem, but actually understanding this and coming up with this equation of motion for B and identifying that that's where the solution for what happens to block A lies is the critical step. Okay, I'll see you in another video. Bye.